this lecture, we move into a more advanced manipulation of rational exponents here. We're going to introduce ourselves more thoroughly to expressions involving terms or factors like a to the m over n power. In other words, we don't have things, simple exponents or expressions like 13 to the 1/3. Now we have stuff like 13 to the 5/3. And so we're going to investigate that. Now, we've already introduced ourselves to this conceptually. That was the first conceptual video for rational exponents. So I'm just going to only review briefly the theorem that dominates this section, and then we'll move into talking about this in further detail here. The prerequisites is that you have to know exponents, laws of exponents, integer exponents, rational exponents of the form a to the 1 over n, and radicals. All these things basically are fair game. You must know all about negative, positive exponents, any type of rational exponents, and you should be familiar with how to convert decimals to fractions. Now, in general, you have some base to the m over n power. That could actually be rewritten as the nth power of that base to the 1 over nth power. This is just working our way backwards. We know how to compute b to the 1 over n. That just is the nth root of b. And then we'd raise that to the nth power. So this is actually the nth root of our base b raised to the nth power. Of course, we could have tackled this a different way. We could have said, listen, instead of, because multiplication is commutative, in other words, I could have, instead of looking at b to the 1 over n raised to the nth power, I could have said b to the mth power raised to the 1 over nth power. You notice that this multiplication, m times 1 over n, is the same as the multiplication in this first sentence up above. But when you rewrite this one, it's the nth root of b to the nth power. So this essentially means that both these statements are the same. That you could take the nth root first and then raise to the nth power, or you could raise the nth power first and then take the nth root, whichever you prefer. I will let you know that, in my opinion, this is the best choice. It's much easier to make a very small number and then raise it to a power, rather than making a large number and trying to find the root of a large number. That's very difficult to do. There's a caveat on this theorem here that I should mention. It's that b must be positive. Now, that's not always true, but for the most part, we want our base to be positive. In fact, if you really want to know why, in what conditions that we can break this rule, it turns out this rule only really has to be true if n is even. Because remember, I had mentioned it in the conceptual video, but the denominator of our rational exponent is our root, and the numerator is the power. So if b is negative, if our base is negative, we're taking an even root of a negative number, like the square root of negative 16, which is not a real number. So that's a problem. So if n is even, then b has to be positive. Otherwise, if n is odd, b is allowed to be anything we want, to be honest with you. So that's just a little kind of heads up there. And I'll try to draw your attention to that as we go through examples. In fact, now that I think about it, maybe I should just throw in an example of what I mean. So let's say you have 16 raised to the, let's say 5/2 power. What this means, according to this theorem, is that, and I'm just going to use my best choice one, is that this is the, remember the denominator is the root, the square root of 16, and then remember the numerator is the power, raised to the 5th power. Square root of 16 is 4 raised to the 5th power, and that will be, I think, 1024. I'm 100% sure about that, actually. I should probably check that. Yes, that's 1024. It is. Whereas if we had said, oh, let's look at a negative 16 to the 5/2 power, well, First of all, notice that the root here is going to be even. So we're taking the even root of a negative number and raising it to the fifth power. That's not real. On the other hand, if you had taken a number like, I don't know, negative 27, and said, I want to know what that is to the 4/3 power, well, that's essentially saying the fourth power of the third root of a negative 27. Well, the third root of a negative 27 is definitely allowable. That's just a negative 3. And a negative 3 to the fourth power is 81. So it turns out that if your denominator is odd, anything can be a base. But if your denominator is even, then the base has to be positive. That's just my justification. Now, as I mentioned in the preview of this, is that you'll have to be able to convert from decimals to fractions. So 625 raised to the 0.75 power is the same thing as saying 625 raised to the 3/4 power. And again, using the theorem that denominator of the rational exponent is the root and the numerator of the rational exponent is the power, I choose to actually write the power on the outside, but you don't have to. I'm going to take the fourth root of 625 here. I know that 5 to the fourth power is actually 625, so the fourth root of 625 is 5. And 5 cubed is going to be 125. Now recall that I said that top method is the best choice, taking the root first and then raising to a power. The reason why I said that is because, well, if you take a look at this example, if you had done this where you said, okay, well, let me take the power first, 625 to the third power, and then I'll take the fourth root of that. Well, 625 to the third power is a huge number. So this is the fourth root of some huge number, which I'm really bad at taking fourth roots of huge numbers. So you could already see that this is kind of impossible, well, not impossible, but very difficult to do. That's why you should shrink a number down first, and then you could raise it to a power. Don't grow a number and then try to take the root. That's just too difficult. It'll give you the same answer, but it's too difficult. Let's try this. 32 raised to the negative 1.6 power. First thing I'm going to do is actually rip the negative off that exponent so that 32 will drop downstairs and the power will now be positive. And then I take a note that 1.6 is the same thing as 16 tenths, right? Because the last digit there is in the tenths place. And I can reduce that fraction, divide both top and bottom by 2, you get 8 fifths. So this here is just 1 over 32 to the 8 fifths power. And a lot of people think you can't do that by hand, but you actually can. It's going to be 1 over, let's see, the 8th power of the 5th root of 32. Try to think of a number when it multiplies by itself 5 times, it becomes 32. It's going to be 2. 2 to the 5th power is 32. So we're looking at 2 raised to the 8th power here. Now 2 raised to the 8th power is actually 256. There we have it, 1 over 256. All right. So you see, like, these exponents, these are called rational exponents, even though they're decimals. It turns out decimals are rational, non-repeating or repeating or terminating decimals are actually representations of fractions. So we can convert these to fractions no matter what. You just have to be good at it. But every once in a while you're lucky enough to get something like 8 raised to the negative 4/3. Rip off the negative, the base drops downstairs, and obviously the exponent becomes positive. And that's just the same thing as saying the cubed root of 8 all being raised to the 4th power. Cubed root of 8 is 2. 2 to the 4th power is 16. So that's 1/16. Each of these problems, all I did was slowly work with the powers, convert them to fractions, make sure they're not negative, that type of thing. Take roots first and then powers second. Now we're going to switch gears. We're going to start looking at some expressions that involve variables here, because all we've been working on are expressions with numbers in them. But often in mathematics, you'll start having to work with expressions involving variables only. So we want to write this in radical form. Now, to be honest with you, it's not very often that we want to write things in radical form. Often we want to write them in exponential form. But this is a good practice anyway to get used to the notation. So first thing I'm going to do is follow the order of operations, look on the inside of the parentheses. If you can simplify anything in there, please do, but you can't. The second thing I'm going to do is rip the negative off the exponent and drop that stuff downstairs. So that picture drops downstairs and the exponent becomes positive. And remember what I said, think of things in mathematics as pictures. This is just a picture raised to the negative 4/7 power. When you rip off the negative, that entire picture drops downstairs. And again, our goal here is to write this in radical notation. That 7 in the denominator of the exponent means we're taking the 7th root of xz, and we're going to raise that result to the 4th power. That's perfect. That's a perfect format right there. Some people might want to have written that differently. Some people might want to say, oh, that's like the 7th root of x to the 4th power, z to the 4th power. That's actually true as well. So it doesn't really matter which way you write it. They're both equivalent. Now you look at something like this, negative 5 s to the point 8 y to the power of 1.2. And there's going to be a couple things we're going to do here. One, I want you to notice that the powers, these exponents, are only touching the variables. They're not touching the negative 5. So no matter what we do, we will always have a negative 5 out front because nothing's going to move that up and down or change its number. The s to the point 8, that's 8/10. And that y to the 1.2 is 12/10. And of course, we can reduce each of those fractions. It's negative 5 s to the, let's see, those are both divisible by 2. That's a 4/5 power there. And y, those are both divisible by 2. That'll be the 6/5 power, which is actually somewhat interesting. There's an argument that I think a lot of people could make here. The idea of a simplified radical expression is not really a huge deal to me, but I think it is kind of important for a lot of other instructors, so I should probably note this. Maybe I'll write this down right here. So as succinctly as I could possibly do it, if you want to simplify a radical expression is said to be simplified if the following three things are kind of true. There's actually some authors tend to want you to have rationalized denominators, which is something we're not talking about right now. And in fact, several of these things we're not really talking about right now, but I don't usually include rationalizing denominators in simplifying radical expressions because that's a throwback to the days when we didn't have calculators, which I'll explain when we reach that lecture. But at this point, a radical expression is said to be simplified if 1, each factor in the radicand is to a power that's less than the index of the radical. So remember the structure of a radical. You have like the nth root of b or something like that, and you might have a power p in here. This object that's in here, the b to the p, is called the radicand, and that n is called the index. This symbol is called the radical. Okay, so each factor in the radicand is to a power that's less than the index of the radical. In other words, we take something like, let's say we're looking at the third root of 5 times x to the second. That's perfect because the power on x, which is 2, is less than the index. We'd have an issue if we had something like the following. Let's say the fifth root of x to the 6th power. That is technically not simplified. You can actually, we'll talk about in a future lecture how to simplify these. It won't happen, it won't be an issue in this lecture, but we'll talk about in a future lecture how to simplify these down. But it's just important to note that this is not considered simplified because the power in the radicand is higher than the index itself. But again, something very easy to rectify in the future. The radicand contains no fractions or negative numbers. In other words, we don't have stuff going on like this, like the third root of 1/4 or something like that. That's illegal. We don't like that. It's much easier to say that's the third root of 1 over the third root of 4, or better yet, 1 over the third root of 4. And finally, and this is the reason why I wanted to bring this up, is if you have stuff like, oh, I don't know, the fourth root of x times the fourth root of y, we tend to like to glue those together to call that the fourth root of x times y. Okay, so if you have neighboring radicals multiplying and they have the same index, then you can glue them together. That's the reason why I actually had to do this aside, is so that we can then take on this example. So in this case, I just have to change my pen color here. We have a -5, and then if you look at this, that's the fifth root of s to the fourth power. And I'm writing it this way because I'm going to combine radicals in a moment. And we also have a neighboring factor here, the fifth root of y to the sixth power. Now, since these are both fifth roots, I can combine them. That would be considered simplified once I do that. So this is going to be -5 times the fifth root of s to the fourth y to the sixth. That would be completely simplified. Now, some people might ask me, why, how would I have known to write it like that, since you've been telling me this entire time to write it like this, the fifth root of s to the fourth power? How would I have known to rewrite it the other way? Well, generally, when you're working with expressions involving variables, you tend to actually write the powers on the insides. Okay? So when I say that back here, that top method here is the best choice, it's the best choice technically when dealing with numbers, when computing with numbers, I should say. But in reality, if you're dealing with variables, that second one is the best choice. Best choice with variables. It's just because it allows for simplification a little bit better. That's all. So let's go back to our example set here, and I hope that makes sense to you. If it doesn't, go ahead and rewind this and try it out a couple more times, see if you can kind of get it. So now we're going to go into some examples where we're going to write things in exponential form, which is technically what we really want to do in the long run. First thing to note here is that -6 and that x upstairs don't have exponents other than 1 on them, so they stay upstairs. In the denominator, I have a y. I see I'm taking the fifth root, so remember, that means when I write it as an exponential form, the 5 is in the denominator, and it's the seventh power of it, so that means that 7 is in the numerator. And there you have it. You have -6x over y to the 7/5. Now I should note here, let's consider that all variables are positive. That's actually kind of important here, because I might give you an example that involves a variable that I'm taking the square root of. And so if you don't know if the variable is positive, you don't know if you can take the square root of it. Also, I have to state that they're positive or at least non-zero because I'm dividing by y here. And if y is 0, I'm dividing by 0. That's just to be technical. Let's try another one. And I just thought of something before I start this next one. Negative exponents for your answers might be fine. Maybe your instructor's okay with that. If that's the case, then you could rewrite this last little bit as -6x. You could put a negative on the exponent here, and that would move this into its opposite position, or in other words, its reciprocal position. So it would move the y upstairs, but you would now have a negative exponent on it. So you'd have something like that, which is absolutely fine. They're both the same. This next example is kind of a weird looking example. You have 2w being divided by 5 times the square root of capital V times z to the 7th power. My handwriting's a little bit bad in here, so I apologize. And all I want to do is rewrite this in exponential notation. Well, the numerator, 2w, only has exponents of 1, so there's not really much I'm going to do there. The 5 also is kind of hanging out. But this VZ business, VZ to the 7th business, that's being raised to the 1/2 power. That's what a square root is, right? It's just a 1/2 power. And it's a little easier to deal with this problem like this because you could see I could then apply the 1/2 power to V and also to Z. The numerator still remains as 2W. The denominator is 5, V to the 1/2, and then Z to the 7/2. That's using the law of exponents that I can multiply powers to powers. And that would be the answer, unless you really want to write your answer using negative exponents, which is absolutely fine. You can. That'd be 2W over 5. I'm not going to put a negative exponent of 5. That's ridiculous. V to the negative 1/2, Z to the negative 7/2. But again, I personally like the stuff in green there, that it's the positive exponent business. Doesn't really matter, honestly, the same thing. But this problem specifically, part B, is why I had to mention all variables are positive, because I'm taking the square root of V there. If V was negative, I couldn't take the square root of it. There you go. Kind of going along in the same vein, all we're doing is all the computational stuff. The next video I do will have more advanced topics in it concerning this specific idea. But for now, we're just doing all the mechanical stuff so we can get used to the idea. So if you see this, a negative cube root of 27 to the 4th, a lot of students will actually take 27 and raise it to the 4th power, which is ridiculous. You get some huge number. So I want you to remember that this is the same thing as saying negative 27 to the 4/3 power, right? The root is 3, the power is 4, which means that I could have rewritten this as a negative and then the 4th power of the cubed root of 27. Sorry that you can't see my cubed root there, but it is there. So this tells me I'm looking at a negative and then the 4th power of cube root of 27 is 3. And 3 to the 4th power, well, that's 81. So my answer is a negative 81. Remember, see that the negative is hanging outside the entire time. So nothing affects that negative. It's just going to sit out there the entire time. There's no power on it or anything like that. It's just waiting for the final answer to be written right in front of it. So it's a negative 81. Notice how much easier it was to take the cube root first and then raise it to the power. And that goes along with what I said earlier, that when you're dealing with numbers, computing with numbers, it's better to put the power on the outside and take the radical or the root first. And here's a strange one. The 5th root of 32 to the 4th power times x to the 15th. And by the way, all that stuff is underneath the radical. Well, I kind of hinted at it a moment ago in an earlier definition, this one right here, that you can break apart. This says right here that you can break apart a radical. So let's go ahead. There's a condition on that break, but I'm not mentioning it here. For now, we're just going to go ahead and break this part. We're going to break this part to the 5th root of 32 to the 4th power times the 5th root of x to the 15th. And actually, now that I'm thinking about it, using this theorem, it might not be so natural to some people. It might be more natural, in fact, to have rewritten this as the 1/5 power, actually I think this is much better, of 32 to the 4th power times x to the 15th power. Now that I'm seeing it, that's actually a much better way to rewrite this, because now I can apply this power to each of these factors. So I'll have 32 to the 4 times 1/5, or in other words 4/5 power, and x to the 15 times 1/5, or in other words the 3rd power. Well, the x part pretty much solves itself here. And the 32 to the 4/5, I'm going to take the 5th root of 32 first, if I can. And then whatever that ends up being, I'll raise that to the 4th power. Remember, I have that x cubed sitting on the outside. Well, the fifth root of 32 is 2, and 2 to the fourth is 16. So that's just a fancy way of writing 16x cubed. Yeah, I like that approach better than splitting this radical. So I'm not going to do that splitting the radical for a while. I like just raising it to the rational exponent power and then applying the rational exponent to each of the factors. In this last example for this example set here, we have a negative, and then I'm going to convert that again into something with a rational exponent 1/4. I have 16 x to the 12th, y to the 16th. And again, using the law of exponents, we can apply this 1/4 power to each of these factors. So that'll be a negative 16 to the 1/4, x to the 12th to the 1/4, but remember powers to powers multiply, so that's x to the third. Y to the 16th to the 1/4, but again, 16 times 1/4 is 4. And now I'm looking at negative 4th root of 16, x to the third, y to the 4th, or in other words, a negative 2, x cubed, y to the 4th. After a while you stop, putting these in radical notation. You start thinking, what's the 4th root of 16? That's 2. So you don't have to convert it to radical notation to do that. Now we get into a couple of evaluation problems where, honestly, I know right now that I can't take these powers without a calculator. So generally, if that's going to happen, if you reach a number where like 5.3, that's just not a number that's a perfect square, perfect cube, perfect anything, then I immediately think, okay, calculator time. Now, I've been very calculator heavy for the TI students, the students who have been using TI graphing calculators. But let me go ahead and show the other students who do not have access to a TI how to use Google as your calculator. Now, we have done a lot of problems where we've needed a calculator. And in this problem set here, we have 5.3 to the 2.9 power. So to enter that into Google, you write 5.3, and then you raise it to the, and start a parenthesis, just like you're using a graphing calculator. That raise, by the way, is called a caret. Raise it to the 2.9 power and end your parenthesis. Google's a calculator. It'll immediately tell you it's 126.008552. You can get even better with the calculations here. Now, honestly, there's even a better calculator out there. There's one called Wolfram Alpha. So let me go there. And you do the same thing. 5.3 raised to, and again, parentheses, 2.9 power. Now, honestly, you don't have to use parentheses on the 2.9 power, but it's good to do. And you notice that Wolfram Alpha actually gives you a better approximation. They give you more digits. And notice when I hit enter, it actually does round it. You can click more digits if you want, and it'll give you something with a ton more digits on it. But let's go ahead and round this to the nearest hundredth. So let's do 126.01. So I'll just write this in here, roughly equal to 126.01. Now this next one, in order to put it into any calculator, I'll have to convert it to rational exponents. That's 6.2 to the 3 power in the 5th root. So 6.2 to the 3/5 power. Let me type that in here, 6.2 raised to the, start a parenthesis, 3/5 power. See, it's immediate that it comes back with that, but I'll just hit enter anyway. I'm going to round it to the nearest hundredths place again. So that's going to be 2.99, roughly. There we go. So there's a couple options for you if you don't have a calculator on hand, if you're working on a laptop, something like that, and you have internet connection. Wolfram Alpha is a great source. That's Wolfram, Wolfram, Alpha. Oops, there's an L there. Alpha.com. Finally, I'm just going to do a couple examples here of simplifying fractional expressions with rational exponents. And this is just still following the order of operations here. So again, the order of operations says, listen, deal with the numerator first, clean anything up there that you can, which there's nothing to clean up there. And then deal with the denominator second, see if you can clean anything up there. Once you've cleaned up numerator and denominator, now clean up between the numerator and denominator. So in other words, is there any like factors that will cancel? In this case, 4 goes into 32 8 times. That's great. Also, it turns out that x to the 1/3, well, these x's share the same base. So there is a law of exponents that we can take advantage of here. The law of exponents is that the power in the numerator subtracts the power in the denominator. Now remember when I was doing this before, I would say, oh, the denominator has a power of 5 and the numerator has a power of 1. Who wins and by how much? It's not so easy to say that when you're dealing with rational exponents because it's just really not easy. So you might have to go about it this route. So here we have 8x to the negative 4/3. And let's not write our answers with negative exponents. Let's write our answers with positive exponents. So let's rip off that negative. And remember, the base of that exponent's only the x, so that drops downstairs, and I have a 4/3 power there. That's the simplified version of that fraction. In this next example, it's a little more complicated. Not so much more, but just a little. First, I'm going to look upstairs in the numerator and see if anything will combine or simplify, and it doesn't. Then I'll look in the denominator and ask the same question, and again, in the denominator, nothing cleans up. So now I look between the numerator and the denominator. Well, 3 and 7 don't cancel, so I'm going to rewrite those. They're just kind of stuck. And then they both have r's, so I'm going to have r to the 1/6 minus 2/3. And they both have z's, so I'll have a z to the 2 minus 1/5. Remember, that's using the law of exponents that we talked about. The law of exponents that we're using here is that b to the m over b to the n is equal to b to the m minus n. Okay. Now, notice there's just some fractional arithmetic here. So let me rewrite this. I have 3 over 7. In the numerator, I have r to the 1/6 minus, and then I'll get like denominators here, so that'll be 4/6. Z, let's see, I need this denominator to be 5, so that'll be 10/5 minus 1/5. And again, these are prerequisites, so I'm not telling you how I'm doing it. I'm just doing it. And this will simplify down to 3 over 7. Let's see, r to the 1/6 minus 4/6 is negative 3/6. Z to the 10/5 minus 1/5. Well, I had 10 of them. I'm losing one of them. I have 9 of them. Now, I know that that fraction 3/6 will reduce to 1/2, and also I can rip the negative off of that exponent. So let's do that. Let's write this as 3 over 7. That r I'm going to pop downstairs and rewrite its exponent as positive 1/2, because that's what 3/6 is. The z, on the other hand, will stay upstairs because it's positive already, so we'll just leave that like that. Now, there are tons of problems involving simplification of fractions with rational exponents and that type of thing. The best way to actually learn how to do this is to do a ton of problems. You just get used to the operations after a while. I want to reiterate, all we're doing is following the order of operations and the laws of exponents the entire time. I know that you have a textbook that gives you chapters upon chapters of new material, it seems like, but they're all the same material over and over again using the order of operations. So I want you to try to think of things simply and not overcomplicate them. That's the worst thing that all of us tend to do as human beings. So anyhow, that's it for this section.